Okay, this is very unlucky because you all want coffee, so we'll try to be quick and less boring as possible. So I'm Salvatore from the University of Tokyo, in Japan, from the Iwasaki Lab. And today I will talk to you about the development about SonicParanoid. SonicParanoid is a tool for predicting orthologous genes de novo. Basically, de novo means differently from, basically means it's not a database, and the prediction are done directly on the proteomes that you give in input. All these de novo tools, they have many things in common, but two of the important things are they all require all versus all alignments, and they also rely usually on the bidirectional best fit for predicting the orthologs. These two things causes many problems, but two main problems. So the alignments are extremely lengthy, and which affects basically the scalability. Scalability means that it will work maybe with 50, 100 proteomes, but then if they are very, very, very many proteomes, then it will never finish. And the second problem is that, among the others, using the BBH, you cannot predict orthologs at the domain level. And I will go in detail soon. First, let me show you the dataset I use in these results. Two datasets. There is the 2020 version of the Quest for Orthologs, the benchmark dataset, and there are 78 proteomes. And I created another one from high-quality mags, 2000 mags, prokaryotic mags. And I used the cluster with 128 CPUs. So let's go for the first problem. How do we reduce the execution time and increase the scalability? So when you have, for example, two proteomes, you need to do the interproteome and intraproteome alignment. So interproteome alignments are AB and BA, right? These two things, independently from the aligner you're using, they can have very different execution times. So basically what we do, what I did, basically I trained this AdaBoost model that would tell me in advance which one would be the fastest. And after I do these predictions, I run those that I call fast alignments, and also the slowest, this the interproteome alignments. After this, as we think yet again of AB, we know already what is inside AB, and based on the way BBH works, I analyze the output, and basically I can know if there are sequences that would never be orthologs. So basically I will remove from A and B. So the second part is run on a subset of the original input, and we save a hell of a lot of time. And well, the last part is the whole SonicParanoid. We predict the orthologs from that. So results on this part, basically we half the execution time. There is no degradation on accuracy, which is very important and is very scalable, as I will talk about more later. And it could be used also by other graph-based methods, which I think is also nice. And so now we move to the second part about domain-based orthology. And the first thing we do, we want to construct basically the architectures, the domain architectures, right? And we use MM6, we search on PFAM. We do n searches in this case, one for each proteome, okay? And then we built these architectures with the domains. Now, I want you to forget about biology for a second and think of architectures as phrases and domain as words, basically. Right? And these things are what is called the corpus for training our Doc2Mec model, which is Doc2Mec basically what came just before transformers. So it's Doc2Mec because it's way more efficient. And after we have trained this model, I take all these architectures, right? And I use Cousin similarity to see how similar or not similar they are. So I found my putative orthologs, and then I do the prediction again and predict the pairwise orthologs. So to give an example why this is important, for example, if you see, the study was basically an example is in Domainoid, which is another method. And basically, there is an example of fusion in which basically these two sequence from E. coli, there was a fusion event, and they created the eukaryotic uridine-cytidine kinase, right? And if you see the bottom in here, this is how we look in the model. So these are the architecture for each of the sequences, and the orange is the Cousin similarity. Well, just as a toy test, we just used the QFO, the sequences in the QFO, and we found the extra 17 of these eukaryotic orthologs, right? So we found this fusion 17 times in 12 different proteins. And so the second problem, yeah, we can find domain level orthologs, sorry. this scary thing is the whole pipeline. If you see on the top is the graph-based, the bottom is the domain-based. And what I didn't tell you is that these are then merged in a very boring way. But once we have this, there you have the ortholog groups using MCL, which is what in the end people will use, right? So speed. So we compare this to OrthoFinder and Broccoli. OrthoFinder is also a graph-based method, and Broccoli, it tries to reduce execution time, but in a different way. And we were up to 18 times faster than OrthoFinder. And when we think about how much we increase the recall or the number of prediction, we've seen on the QFO, and the results, it's in most of the tests, especially at low sensitivity, is doubled the recall. And scalability, yes, scalability basically took 24 hours for 2,000 mags, but mags kind of, I think, they are not very big, right? So it's kind of a toy the way I see it. But then there was the Spanish user that she was able to run it in 1,000 huge proteome. So that was, let's say something about the scalability. The other tools didn't finish. And this is the important part. And we are saying that we are the most accurate on the QFO20 challenge. And basically, this is a very nice tool from the community that allows people to test all the methods. In this case, there were 15 methods competing and 12 benchmark tests. And if you look at these figures, the thing is that these are only 4 of the 12 tests. If you look at the figures, basically those that are close to or on the Pareto frontier, they are supposed to be the best. But you will agree with me that if you look at this, you cannot tell that I'm the best, right? Because I don't. It's difficult to tell, right? So the nice thing is that the benchmark also has free classification method that separates the results in groups. So first, second, third, fourth, and the first one is the best. And then I did this hopefully more easy to understand thing, which I like to call the orthology inference Olympics. The idea is because basically if you look at the colors, like group 1, 2, 3, 4, it's like the medals. So those that get the best number, gold, silver, and bronze, then the highest, right? These are only 10 of all the competitors because it's much bigger. What I like of this figure for me is that, especially this part in here, basically this purple thing here is the SonicParanoid2 using only the graph-based, not the domain-based. And if you see, this one is the previous version of SonicParanoid. So that means that these are comparable, and our way to reduce the alignment time, the alignment time doesn't affect the accuracy at all, which is a good thing. And this is, I know this is a bit, sounds like bragging, but let me finish. So, okay, for now, I would say that we are fastest. It's a very comprehensive, most scalable, most accurate, and I'm going to say that it's until the next challenge because it's already starting. So, and the competitors are a lot and are very strong. So I'm sure that we won't be there. We will be at the challenge, but we won't be on the top, I think. And now it's time to thank people. So people at Iwasaki Lab, what are they sitting there, and friends and competitors from Quest for Orthologs. And yeah, the early users, because they helped me a lot. And well, if you have time, just take a look at the preprint after the coffee because it's long and boring. And then if you want to come later to the poster, that would be nice. Of course, I can give you more details in the poster.
Okay, thank you. I think we can have one question.
So you showed that you can get even more orthologs from collections. What about decreasing the number of orthologs? Because if you're looking for G, which could share the same.
Oh, you can, yes. So you want, when you say decreasing, you mean more like something like filtering?
Something which is like the true ortholog.
Oh, yeah, you
as
get
closest as possible, basically.
You can do that. There are lots of options, and the tool that I created myself for playing, but there are some people told me that are actually useful. So there is a way to filter based on the bit score. So if you increase it, that's already a way to reduce that. That will also reduce the memory use for MCL, because MCL, especially if you have huge and lots of proteomes, it would take very long. So that's one way. Another way is that you just go to the output, and I'm talking about the groups now, okay?
Yeah.
The ortholog groups. You already have that the single copy orthologs you can use. So I hope it answers the question.
I think we'll discuss it.
Okay,
Thank you.
please.
Okay.